The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Boyle's Law. Let's just go ahead and read the definition for Boyle's Law once again. Boyle's Law, the product of the pressure times the volume of a gas is constant when the quantity of gas and temperature are kept constant. Or, as we had just previously stated, the volume is inversely proportional to pressure. And the equation is as follows. And this notation here is for constant. Great. Now, if we look here at figure 2.14, we see that as the pressure is increased, more specifically increased from 1 atmosphere to 2 atmospheres, thus the pressure has doubled, the volume now, that's going to be halved, right? It goes from 4 liters to 2 liters. And the same relationship applies in the opposite direction as well. Now, if we take a look at figure 2.15a, where we have volume plotted for pressure for a mole of gas at a constant temperature of 0 degrees Celsius, we see that we have a curve being produced here, and that is once again due to the inverse relationship of pressure and volume. Now, if we wanted a straight line, we can obtain a straight line. If we take a look at figure 2.15b here, we see that we have the plot of volume versus against the reciprocal of pressure here. And we have a straight line. Now, what do we think is the slope for this straight line here? Well, to answer that question, we can take a step back, come up here to our equation, and we can rewrite our equation here in the slope-intercept form, which is just going to be as follows. Now, this follows right from y equals mx plus b, and if we recall, b is the y-intercept, right? Here it is x, and the m is our slope, which is going to be the constant here as such. Now, should you require further review on the slope internet form here, as we see, we covered it quite extensively in the temperature lecture. It'd be a good time for you to pause it and visit that lecture now. But for the rest of us, let's continue on. Looking here at our last point, when the quantity of gas and temperature remain constant, Boyle's law can be stated as follows. And this equation is very helpful when you're working with various types of problems related to Boyle's law. Great, let's move on now to our next slide here. If we take a look here, example Boyle's law 1. During expiration, air flows from blank pressure in the lungs to the environment and lung volume blank while the pressure within the lungs blank. This problem is going to be a little bit tricky due to the fact that we have multiple blanks. Thus, we'll solve it in portions, working with the first part here. Now, we see the answer for that can either be higher or lower. Thus, during expiration, air flows from higher or lower pressure in the lungs to the environment. It's going to be higher pressure. Thus, we know that C and D are not going to be valid. Thus, now if we look at the next two spaces, we see it goes increases, decreases, or decreases, increases. Now let's read our question here one more time. During expiration, air flows from higher pressure in the lungs to the environment and lung volume increases or decreases while the pressure within the lungs increases or decreases. During expiration, the lung volume is going to decrease, and while the pressure within the lungs increases, and that follows as we had stated from Boyle's law, right? We see here as volume decreased, the pressure increased, right? Thus, we can confidently then say that B is going to be our answer as such. Great, let's now move on to our next question. Looking here at example Boyle's law 2. At a pressure of 1.2 atmospheres, Janus holds a helium balloon with a volume of 2.5 liters. He then accidentally lets the balloon go and it ascends 4,000 meters where the pressure is 0.5 atmospheres. If the temperature of the gas is constant, what is its change in volume? Let's consider this problem for just a moment. Looking here at figure 2.17, initially, since the volume does not change, we know that there's going to be a constant balance between the internal pressure here of the helium gas inside the balloon, right, and the atmospheric pressure. Thus, we can say the internal and external forces are going to be balanced. Now, as the balloon ascends 4,000 meters, it's telling us here that the pressure is going to be 0.5 atmospheres, thus the pressure decreased. Then that means that the air pressure here is not pushing back as much on the balloon as it did at lower altitudes. Thus, due to the fact that there's lower pressure on the balloon, we know that the balloon is going to expand and the change in volume should be positive. Let's take a look now, and we'll use Boyle's law to find out if our assumption here is correct. We'll begin with our equation as follows. P1 V1 equals P2 V2, and we're looking for V2, right? Thus, our equation becomes as follows. Now, excuse me, that should be P2 there. Now, if we go ahead and we plug in our values, we were given P1. That was just going to be right there, right? 1.2 atmospheres. And we're given the initial volume, which was just 2.5 liters. If we take a look at the top. Now, if we go ahead and we divide that by our P2 here, which was given to us as well as 0.5 atmospheres, we find that the final volume is going to be 6 liters. Now, are we done? No, we're not done. And why is that? That's because we're being asked for what is the change in volume, right? This is just going to be the final volume. Thus, to find the change in volume, we're going to have to use the following equation here, where V2 minus V1. And we know V2 is going to be 6 liters, and that initial volume was 2.5 liters. Thus, that change in volume is going to be 3.5 liters as such. Thus, C would be our best answer there. Great. Let's now continue to our next slide.